Here we have the work energy theorem, which we developed in some detail last time. And the point I'm trying to make is that if you have non-uniform acceleration, you can't use the equations of uniform acceleration. Example of non-uniform acceleration, I drop a Nerf ball, okay? Air resistance. Air resistance depends on velocity. Velocity depends on time. Acceleration is not uniform in time. Okay, so you can't use equations of uniform acceleration, for example, for the problem of the mouse going down the well. Okay, where the kinetic energy of the mouse is less than you would expect from an ideal drop of the same distance. Difference being what you try to find. Okay, I'm sorry?
Would you use those equations? The equations of constant acceleration?
No, you can't.
Yeah, would you use them to calculate the ideal?
No, you just take the change in potential energy. Why would you go to the equations of uniformly accelerated motion when you know the force and the distance? You know the mass of the mouse. Why would you use uniform acceleration to do something you can do with one step if you have chunked your knowledge into a set of compartments where potential energy is one of them, okay? Now, of course, that's what we're trying to achieve, right? It's not natural, and everybody wants to do it, which is why I'm digressing for a whole class for these two examples, okay? Make sense? Now, similarly with a pendulum, I'm going to, it's a little more complex to analyze for the pendulum because we've got to go back to figure out the force constant and all that stuff, okay? So we draw the forces on the mass of a pendulum, and we put them in a free body diagram, and we notice that the tension is sum of a y and an x component. And we make the assumption that the pendulum moves in the x direction, which is not really true if x is horizontal, because the pendulum moves perpendicular to the radial line because it's moving in a circle. Okay? So we have an inaccuracy here, so our analysis depends on theta being small. Okay? Well, anyhow, theta is small, so we can do this. Our gravitational force is negative mgj, and our tension resolves into ty times j plus minus tx times x, right? Or plus tx times x, but we'll figure out that tx is kind of negative, and that turns out I really didn't do that, did I? No, actually, I didn't do anything that would contradict that. Okay, so net force is tension force plus the gravitational force, which is T vector minus mgj vector, right? Now our hypothesis is, again, not completely accurate, only accurate if theta is small, that the motion is in the x direction. Motion is horizontal. It's kind of what it looks like, kind of what it feels like, not completely true because of what I just said. Meaning that that's going to be some multiple of the I vector. The net force is going to be a multiple of the I vector. Okay? So we just write the tension is Txi plus Tyj, and we see then that we have two j components, Tyj and negative mgj, that have to add up to 0 because there's no j component on this side. Meaning then that Ty minus mg equals 0, so we know that Ty equals mg. Magnitude of Ty is mg, okay? Not really true, but if theta is small enough, it's practically true, okay? So, of course, Txi is just what it is, Tx times I, right? So the net force is just Tx, and I should put arrows over that, so that the tension is your Txi plus Tyj. Okay? Not exactly true because of our assumption of horizontal motion, but for small theta, close enough for good approximation. we analyze the forces here as we've done before. If we just do our t vector, if this is theta, then this angle is 90 degrees plus theta. And ty is just t times the sine of 90 degrees plus theta, a little hard to read. Tx is t cosine 90 degrees plus theta. Using the circular definitions, not triangles, tend to cause errors in sign. You've always got to be thinking about whether this thing's positive or negative if you use triangles like you do in statics, right? Now you got to be able to do that because the triangles are nice and intuitive, so it's not a bad thing to be able to do. But in this course, we're just going to use the circular model whenever possible, okay? Because it takes care of the plus and minus. Well, your Tx then turns out to be negative t sine theta because the cosine of 90 degrees plus theta is negative sine theta. And your Ty is t cosine theta because the sine of 90 degrees plus theta is cosine theta. Okay? So we get the right sign on this thing that your Tx is negative, and the way the picture's drawn here with a positive theta. Okay? And we have this. Now, I'm not going to make the connections because we're running very short on time, but it follows from this that your net force on the pendulum is negative Kx, where K is mg over L. Okay? Now, when you multiply negative mg over L by x, you get an x over L, right? What's x over L? Well, x is this, L is this, and x over L is just the sine of theta. Okay? And the sine of theta is close to theta, so t sine theta is close to t times x over L. Now, I said it, I didn't write it out, so you're not necessarily responsible for remembering it, but I have talked about the small angle approximation for sine and tangent. Okay? And that's something you do want to kind of use whenever you can, whenever it's appropriate. Okay, well, then we look at the net force. Well, we're trying to figure out the work that's done as you move from position xi to position xf. Okay? So just, this pendulum, some position from xi to xf, where again, x is always small, much smaller than L, so the theta is a small angle. Okay? Then we see that, graph, according to this, we're going to have a linear force versus position graph because this is linear. Meaning that the average force is the average of the two forces, okay? We multiply that by the displacement from here to here, and we get the work done. And that's going to be this. That's our change in kinetic energy. Work done on the system by the force, right? And that's equal to the negative of our change in potential energy if we assume there are no dissipative forces. And that's true if we define potential energy as 1/2 kx squared. Okay? Now the point I'm making that I don't have time to complete. Okay, here you've got K. And we've got this pendulum that we're going to, of length 60 centimeters, we're going to release 10 centimeters from equilibrium, find out how fast it's going at equilibrium. Well, we can evaluate K very easily. If you take my word for it, it's mg over L, and I just told you why, but I didn't write it out, okay? But it's because of this and the small angle approximation for theta. Okay, so here's K. If we release at 10 centimeters from equilibrium, then xi is 10 centimeters, xf is 0, right? So that our delta Ke, which is, and after all this stuff about xi and x0, somebody wanted to use x0, so I wrote down x0 without thinking it's xi, right? Okay? So it's 1/2 kxi squared minus 1/2 k times 0 squared, which equals 1/2 m times 16 reciprocal seconds squared times 0.1 meter squared. Okay? Well, what are the units going to be? Now I've got an m for mass and an m for meter, but from context we can tell the difference, right? M's going to be in units of mass. This is going to be in units of meters squared over seconds squared, right? So this is going to be in units of energy, isn't it? Mass times meters, length squared over, okay? So this is going to be like 0.08 m, where m is mass, times meters squared per second squared, keeping track that this is meter, this is mass, right? Maybe I should use capital M. So the velocity is 1/2 mv squared. Sorry. Kinetic energy is 1/2 mv squared, right? And the kinetic energy at this point is the change in kinetic energy if we release the thing from rest. So we have this, our m's divide out our masses, right? This m is a mass, this m is a mass, and we get v equals the square root of 0.16 meters squared per second squared equals 40 centimeters per second, or 0.4 meters per second, okay?